So we've now looked at the beginning of data instructions in ARM v7. We've specified the instructions that we can choose from. We've specified all the different options for conditional execution of those instructions. And we've specified two registers, a destination and one of the sources. Now we need to go into a bit of detail about how to specify the second source register. And in fact, you have some choice here. You can specify a register by itself. You can specify a register shifted by some amount. And you can specify an immediate value. All of that's done in 12 bits. Now, if you remember from MIPS, specifying an immediate value, you had lots and lots of space, right? You had 16 bits of space to specify an immediate value. Here you've only got 12, which means theoretically you've only got, well, what's 10 to the 12? 10 to the 10 is about 1,000. 10 to the 2 is about 4. So only about 4,000 possibilities of the immediate values, right? But 0 to 4,000 doesn't seem like enough. I mean, sure, you'll get most of the small numbers, but if you had to do something that was 10,000, how would you represent the number 10,000? Can't do it in 12 bits. So how will we do that? We'll see. And then you're going to specify the different shifts. So we're going to either do a 12-bit unsigned immediate operand, which is encoded, again, in a really clever way. ARM v7, very clever. Or a shifted operand. So we'll look at both of those. So first we're going to look at that immediate value because it's clever, it's interesting, and immediate is the most common other thing. Shifting is useful, and we'll do that a lot, but immediate values are a thing we're going to use a lot, right? You want to add 1 to a register, subtract 1 from a register. You do this all the time in indexing, right? Here you're going to start at the beginning of an array, and you're going to sequentially access the bits of the array or the data points in the array one at a time. You're going to add some number of memory elements based on the size of each element in the array. You're going to do that over and over and over again. And that's an immediate value, right? If it's a regular word in an array, you're going to add 4 over and over and over again. So immediate values, very, very useful in assembly language. So how does ARM get away with only allowing 12 bits to specify an immediate value? Well, here we go, and it's super clever. So what it does is it's worse than that and better. So it says you can store the immediate value in 8 bits. And then it takes the remaining 4 bits and allows you to take those 8 bits and put them anywhere in a 32-bit number. It's really, really clever. So you say, so 0 to 4,000-ish is not enough, right? And ARM is going to say you're going to actually store data value in 8 bits, and then you're going to shift those 8 bits around in a 32-bit number, and that's how you're going to make other immediate values. Okay, so you're going to take these 8 bits and you're going to shift them around. It's essentially a simple floating point representation, right? Because instead of saying those 8 bits start at 2 to the 0 to 2 to the 7, you can say those 8 bits start at 2 to the 6 to 2 to the 2 to the 14. Right? Or 2 to the 10 to 2 to the 17. Or whatever, right? You can put those 8 bits wherever you want to put them. And so it's essentially floating those 8 bits somewhere in the 32-bit number. It's quite clever. The actual function looks like this. The immediate value shifted by the alignment, which is essentially the immediate value rotated by the alignment. And it's actually done by 2 times the alignment, and we'll see why in a second. With everything in ARM, it's a little more complicated than you'd like. So here's an example. We want to encode the number 4080. We want to add 4080 to whatever's in R2 and put the result in R1. All right. Add if the previous instruction was equal and store the result into the CPSR. Take R2 and add 4080 and then put that into R1. Now, in ARM, we're going to specify that this is an actual literal and not some other encoding using a hash. That means literal, or in this case, an immediate value. That immediate value is going to be 4080, and we're going to want to put 4080 into that register. Well, if you do the math, if you figure out what 4080 actually represents, this is the binary encoding for 4080, 111111110000. We can't fit that into our 11-bit number, into our 8-bit number even. So what we do is we take these ones, 1, 2, 3, 4, 5, 6, 7, 8, and we put them into our bottom 8 bits, and then we indicate that we're going to rotate that by 4. Okay? We're going to shift that to the left by 4 to put them in the right place. So our immediate rotated by 2 times the alignment. Why 2 times? We'll get to that in a second. So the alignment value is actually 2. 2 times 2 is 4, rotating it by 4, and so that's the encoding. Now, I'm going to give you a minute. I want you to pause the video here and try that with the number 511. You want to encode 511. You want to add 511 to some number or whatever, and you want to encode that in this new format. And again, don't forget the way this format works. Let's do an example here, and then we'll do your 511 example in a minute. So let's encode the number, well, I don't know. The trick is small numbers don't need an alignment, right? If I want to encode the number 1, right, what is binary 1? It's 1, 0, 0, 0, etc., right? That's the number 1 in binary. And so I take my 8 bits, right, and it's 0, 0, 0, 0, 0, 0, 0, 1, and I want to move those around in the 32-bit number, right? Here's the 32-bit number. So 0 to 31. Well, I don't need to move them because they're in the right place. And so my alignment is 0. I'm not moving anything. Okay, so what if I want to encode the number, well, what's a nice power of 2 that we could use? 2 to the power of 20. 2 to the power of 10 is about 1,000. 2 to the power of 20 is about 1,000,000. So 2 to the power of 20, which is about 1,000,000. Oops, that's too many zeros. About 1,000,000, whatever it actually is. So we're going to encode 2 to the power of 20. Well, what we want to do is we want to put this 1 at the 20th position, right? So now what we're going to do is we're going to take the same number, 0, 0, 0, 0, 0, 0, 0, 1, and we're going to align it, oops, A-L-I-G-N, with 20. And now you'll see why we actually need to use 2 times the alignment to move things around. Because we only actually get 4 bits for the alignment, but a 32-bit number can be encoded in 5 bits. And so this is, again, one of these trade-offs. We could have just used 5 bits. We could have said we're going to use 7 bits for the value and 5 bits for the alignment. But it's determined in the design of this system that it's more valuable to have 1 more bit of value than 1 more bit of alignment. Because we can take this 1 and put it anywhere, right? We can use our alignment value to put it anywhere. So, for example, we're going to put this alignment at bit 20, which means we're going to encode 10, and we can encode 10 in 4 bits, right? What is 10? 10 is 8 plus 2. So that's 10. And so our full encoding is alignment of 10, which actually means 20 because we're multiplying by 2, and then our 8 bits of value. So now what if we wanted to encode 2 to the 21? Well, we could take that same 1 and we could try to move it by 21, but we can't because our alignment has to be even because we're storing half the value of the alignment in that 4 bits. So instead, what we say is we're going to take 2 to the 20 and move it like this. It's still going to be 20, but the value instead we're going to store is that value. And this moved by 20 is the same as that moved by 21. So this is why you only need to store an even number in the alignment field, because you can most of the time put some value in 8 bits and move it in the right place, and most of the time you're going to get a reasonable number. With small numbers, anywhere from 0 to 256, you're fine. And then with bigger numbers, as long as you can take these 4 bits and put them somewhere, then you'll be okay. And again, you can actually create any number this way, most of the time using small numbers, and so it takes a single instruction to do that, but you can make a bigger number by taking 2 of these 8 bits and aligning them separately, right? You can take 8 bits, whatever they are. There's 8 bits, and I'm going to put that in the first byte of my 32-bit number, and then I'm going to take another 8 bits, whatever they are, and put them in the second byte. And this one here, the alignment is what? It's 8. So I put in 4, right? And then the next one, the alignment is 8 and 8 is 16. So I put in 8. And the next one, the alignment is 32. Right? So this is how you're going to specify any number between 0 and 4 million, which is what a 32-bit number can be. You can specify any number this way by constructing it out of numbers, like chunks of value. If the number you have only has a small number of chunks of value, you don't have to do it this way. You can put this 8 bits anywhere you want in a 32-bit number. So that's the compromise that ARM came up with when it came to specifying immediate values. And it's a little complicated, but that's okay because usually it's a machine doing this instead of us. But as assembly language learners, we need to do this. So what I'm going to get you to do in the next video is I will solve this problem for you, right? 511 is the number I want you to encode, and give that a try, and we'll solve it in the next video.